Okay, morning. Okay, let's continue on the second order homogeneous ODE. We have a couple of theorems that we haven't finished yet, but okay, so let's just quick review here. Okay. So what we're looking at is second order homogeneous ODE. Homogeneous basically means the input here is 0. Okay. So I think you also need to know that, always remember, y or whatever this derivative term in here is, which involving the derivative of that variable, this is just basically the output, okay? This is output. Okay. And those things on the right side here, those are somehow related to the input, okay? So maybe just a simple input f of t here, or maybe it's a even could be a derivative input here, okay? Okay, so the first theorem that we were talking about is, okay, y1 of t, so let's call this equation number 1, okay? y1 of t is solution of 1, and y2 of t is another solution of 1, okay? Then y equal to c1 y1 plus c2 y2 is a solution, okay, of 1. Okay, so that's number 1 theorem. As I said, I didn't see anything about a particular general. I just see that the y is it's a solution, right? It's a solution. But we do have this concept of this particular solution or general solution. Particular meaning this only is standalone by itself. Okay, and general meaning it suits every situation, right? And the second theorem, okay. Second theorem is an independent theorem. This theorem says about this concept of linear independence. So this is where we start. Given a set of functions, for example, y1, y2, up to yn. Okay, and we're interested in what is the relationship. You know, basically, what's the connection among these functions? Given this set of functions, and consider this k1 y1 plus k2 y2 until kn yn. So basically, you multiply each one of the function with a certain kind of a constant. Okay? Yeah. So those are constants here. Now, if we find that, right, if this k1 equal to k2 up to kn, if these constants equal to 0 is the only choice, is the only option to make this expression equal to 0, okay? To make this k1 y1, k2 y2 up to kn yn equal to 0. Okay, if this is the only choice, okay, yeah, then this set of these functions here, okay, this set of functions are called linear independent. Okay, so I'll explain this a little bit more here. So let's call it LI, okay, linear independent. Okay. So I think it's best that I'll use an example here to sort of illustrate this theory number 2 here. Okay. So let's say I have two functions here. Okay, I have two functions. One is t squared, and the other is 2t squared. Okay. So basically, this is a set, right? This is a set of functions. And what we have here is this is y1, this is y2. Yeah. Okay. So now I wanted to know whether these two things are linear independent or linear dependent, right? Yeah. So how do I know that? So what we do is, right, we form this k1 y1 plus k2 y2. Okay, k2 y2. Okay. So in this case here, it's k1 t squared plus k2 2t squared. Right? Yeah. So then we'll look at this k1 k2 at here, right? So what possible values that we can use for k1 k2 such that to make this expression to be 0? That's the logic here, right? So why don't we just, okay, well, let's let this guy equal to 0, right? Let's let it equal 0. Okay. If I let it equal to 0, so let's look at this expression here. So what do we have? We have k1 t squared plus k2 2t squared. So technically speaking, there is a t squared all here, right? So I can take this t squared out. That's k1 plus 2k2 equal to 0. Okay. So forget about the t squared. Just look at this bracket here. If I want to make this equation or this expression to be 0, that means this k1 plus 2k2 needs to be 0, right? Needs to be 0. And this term is 0, meaning k1 equal to negative 2k2. That's it, right? That's it. So, which means how many options do I have for k1 and k2 in order to make this expression to be 0? Infinite, right? Infinite. And one of the choices, of course, is what? 0, 0, right? 0, 0. So in this case, basically, you have, so they are, right? They are infinite. Okay, infinite k1 and k2 combinations, right? They're infinite k1 and k2 combinations to make, okay, this k1 y1 plus k2 y2 equals 0. Okay, yeah. So just based on this observation, and then looking back at this concept or the definition of the theorem at here, theorem number 2 at here. So that means this y1 and y2 are linear, dependent or independent? If they're linear independent, what's your choice? Your choice is this equal to 0, this thing's equal to 0 is the only choice. Okay, I should see here, right? Constant, if this equal to 0, I should see here, sorry, is the only choice, okay, is the only choice to make this expression equal to 0. Okay, then they are linear independent, right? It's the only choice. But now you have how many? You have infinite, right? So k1 equal to k2 equal to 0 is not the only choice. So which means y1 and y2 are linear dependent. Okay, so this is purely mathematical, right? But if you look at these two at here, if you look at these two functions, what do they look like? They look like each other, right? The only difference is what? Only a scale difference, right? So you see the wording dependency, independency, that's actually where they're from. So they look like each other. They're like brothers and sisters, basically, right? Okay, so that's why they are dependent. Okay, yeah. Okay, so let's see if I have three functions. Square. Okay, if I have three things that are here, right? And apparently this set of functions are also linear dependent, right? These are dependent. Okay, yeah. So essentially, this concept of dependency or independency is a sort of a family concept. So everything within this big bracket, if the linear dependency, they're coming from the same family. Okay, so basically you got mother and father, and so somehow this is the son or daughter, so that can be expressed using a combination of these two. Okay, so that's the linear dependency, and sorry, that's the linear dependency concept here. All right? Yeah. And let's see if I have a visual check here. Let's see, how about this t squared, t cubed, and t4? How about this guy here? Without doing anything, if you just look at this one here, what would you say? They're dependent? These three. Do they look alike? Sort of, right? But this is 2, this is 4, this is 3. Sorry, this is 2, this is 2, this is 3, this is 4. And, you know, technically speaking, they're not from the same family, right? They're not from the same, yeah.
So what if you had like four equations in there and only 2 of them were independent? Would the whole thing be considered independent?
No. You still consider them as a...
So it'd be considered dependent.
That's right, independent, yeah. Okay, so this is just by purely look, right? But usually what you need to do is you need to go over these procedures here. So let's take a look at another examples here, okay? Examples. So maybe let's look at this guy here, okay? Let's just look at this guy here, okay? So if I look at this one here, and I want to see if they're linear independent or linear dependent. So what do? I'll go over these typical procedures like I just did here. Okay, I'm gonna let k1 t squared plus k2 t cubed plus k3 t4 equal to 0. Okay, so we're gonna let this guy. And then we're going to look at the solutions for k1, k2, k3 such that this expression to be 0. Okay, so that's the logic. So if you look at this one here, right, actually you don't have to look further. The only choice that the k1, k2, k3 such that this expression to be 0 is what? Is all of them are 0. There is no other choice. Okay, there's no other choice. So for this one, the only solution is k1 equal to k2 equal to k3 equal to 0. Okay, there's no other choice. Okay, yeah. So basically, when you have this kind of situation in here, you can consider you can solving like this, right? You can consider yourself as a situation like this. So for example, this is 0 here, right? So this whole thing equal to 0. It's like a 0 by t squared, 0 by t cubed, 0 by t4. Okay, yeah. So I have this side equal to the other side, and basically this coefficient needs to be equal to that coefficient. This coefficient that coefficient like that, right? Is that good? Okay. Okay. So because this is 0 is the only solution, and that's this thing here, okay, are Li, okay, and they are Li. Okay, so now let's take a look at another set. Let's look at another set here. Oh, to answer, okay, this is what you're looking at here, right? I think, what did I answer you?
You said it was dependent.
You answered they were dependent, right? Yeah, that's right. Okay, so let's look at this one here, okay? So by looking at this set here, these two look very much like each other, right? Yeah. It's just this one is very different, okay? So technically speaking, you actually don't have to, this is going to be linear dependent, but let's go over this procedure here and check it out, right? So it's basically see if they satisfy that theorem number 2. So we're going to let k1 x squared plus k2 5x plus k3 2x, okay, equal to 0. Okay. So this step, the purpose of this step is we're trying to solve for k1, k2, k3, such that this expression to be 0. Okay? Yeah. And often in time, you can make a little simplification because in this particular case, there are x at here. So this is k1 x squared plus 5k2 plus 2k3 by x equal to 0. Right? Okay. Yeah. Okay, so this one equal to 0, meaning the coefficients k1, the coefficients 5k2 plus 2k3, they are 0. Right? So it's like on this side here, there's a 0x squared plus 0x at here. Right? Okay. So then I have two equations now. So I got two equations, right? So two equations, three unknowns. And the second one here naturally make this k1 to be 0. But the first one, 5k2 plus 2k3 equal to 0. That means how many solutions do we have for k1, for k2 and k3? Infinite, right? So basically, the solution in here is going to be 0, and then something at here and something at here for this k1, k2, and k3, right? k1, k2, k3. So then you go back to your theorem. The theorem says they are only linear independent when the k1, k2, k3 has the only solution 0, 0, 0, right? But now you can see now, yeah, 0, 0, 0 is a solution. However, you can have 0, 1 or something else, right? Based on this connection at here. Okay. So for example, one of the solution is 0. If I plug in, if I plug k3 as 1 at here, then k2 would be what? 5 over 2, right? Negative. Okay. Yeah. So this is apparently not all 0, and that means this set of this function here, right? So they are L, not Li. They are linear dependent. So let's call it LD. Okay. Yeah. Yeah, of course. Thank you. Okay. So that's how you check. Okay. If you can't see it, okay, can't see it clearly, so just go through these steps here. Okay. See if you can find a set of solutions for those cases such that they're not all 0. If you can, that means the set of functions are linear dependent. If you can't, if it basically means the only solution to make the expression 0 is all 0 for the case, then they are linear independent. Okay. Yeah. So this linear independent and linear dependency not necessarily just apply to this set of functions here. They can be a concept, very general concept. See, for example, I have an apple at here, and I have an orange at here, and I have a banana at here. So basically, you have three group of things at here. Okay, you got three groups of things, and then the question is, are the three group of things are linear independent or linear dependent? Right. So what do? You multiply each group with a constant. Okay. Yeah, and you compare basically whether they have a connection there. See, the last question I was asking you guys, how do you determine whether a matrix determinant of matrix is 0? So let's say 1, 2, 3, 2, 4, 6, and then 3, 5, 9. Right? This is a matrix here, and the determinant of this matrix is 0. Because why? Because the second rule is it's a scalar multiple. So then what you can see now is I can consider this is a group of things. This is a group of things. This is a group of things. Right? So three group of things. Then when I multiply each group of things with the constants k1, k2, k3, and then ask ourselves, is k1, k2, k3 or 0 is the only choice to make the three group of things to be 0, right? Yeah. So as you can see, now, of course not. The second one is twice of this one here. Okay, so that means this line here, this rule here is dependent on this one here. Okay, yeah, so that's the concept of linear dependency and independencies. Okay, so that gives us the last theorem now. Okay, yeah, we need the second theorem and the first theorem to talk about the third theorem. Okay. So this theorem basically talking about is the general solution of this second order homogeneous equation. Okay, so general solution of this homogeneous one here. Okay. And the theorem says this. If y1 and y2 okay, are two particular solutions to, let's call this equation number 1. Okay, this is to this equation number 1. Okay, right. This is like the first theorem says, right? So y1 and y2 are two particular solutions to number 1. Now this is the only condition, and if y1 and y2 are Li. So y1 and y2 are linear independent. Okay, so they're not connected. Okay, they're not connected. Then, okay, y equal to cy1 plus cy2. Okay, and then this y equal to cy1, cy2 is the general solution. Okay, is a general solution to this equation 1 at here. So that basically it's a guideline here to guide us how to find the general solution of this kind of a homogeneous second order differential equation here. Okay, so how do we find a general solution? We need to find two solutions first, and we need to make sure that these two solutions are linear independent. Then combine them together, that's the general solution. All right. The proof of this one is very simple. You can take. Actually, I don't have a proof here, but anyway, it's a very simple proof here. The textbook should have it. Okay. Now, any questions? Yeah. Now this y1 and y2. Okay. This y1 and y2, there's a mathematical term here. Basically, there are two solutions. They're linear independent. They are also called solution basis. Okay, they're also called solution basis. This basis concept is a fairly technical math concept here. Okay, so just to touch upon this thing here. Okay, when you have a coordinate system x, y, z, right? When you have a coordinate system x, y, z, this x we call I hat, g hat, z hat, right? Yeah. So basically, actually, this I hat, g hat, z hat in the vector space in this linear algebra, these three things, they are called, that's the key hat, they are called the bases. So this I hat, g hat, and key hat, these are bases. Why the term basis? Basis basically means this is the foundation. I can form anything else based on these three things. See, does that make sense? If I have a point in the 3D space, maybe this is 3, 2, 5, let's say, right? So how do I express this point? It's what? 3i hat, 2g hat, 5k hat, right? So that's what we call a basis here. So this thing here is very similar. So the y1 and the y2 are called the solution basis of the second order ODE here. Why they call it basis? Because you can just simply, like what you're doing here, you can multiply any other two constants that are here and then add them together. The resulted y can be used for any other solutions, right? That's what it's called basis. All right? Yeah. Okay, so now we're ready to go into specifically how to get the solution of the second order ODE here. Okay. Now we're going to start from the easy one here. Okay. So we're going to talk about the solution of a second order ODE, okay, with constant, okay, coefficients. Okay, with constant coefficients. So with constant coefficients, meaning we're dealing with y prime plus ay prime plus by and equal to 0. So a and b are constants. Okay, so this is what we're dealing with here. All right? Yeah. Okay, so let's start from first order first. Okay, if you recall that when I have a first order, like this kind of situation, basically there's no this term here, just this first order term like this. Okay, when we have this kind of here, what's this solution here? Right, this is homogeneous, this is constant, that's pretty simple, right? You can use separating variables to solve this problem in here. Okay, so the solution of this one here is c e to the power negative at. Okay, the solution of this is this. So the solution of this first order, this is a constant. It's exponential decay. Not the necessary decay depends on the value of a. It's exponential function here, right? Exponential. Okay. So then the question here is, if the solution for the first order is an exponential, then could it be also possible that a solution to this kind of second order with the constants here are also exponential ones, right? Yeah. So then what we do is, let's verify that, right? Let's verify it. So verify meaning I'm going to let y equal to e to the power lambda t. Okay, so I'm saying is, well, I think the solution for the second order one are also in the exponential format. Right? Yeah, also in the exponential format. So then let's try it out. So let y equal to this guy here. Consider this guy as a solution of this, right? As a solution. So what we do is, let's let this guy then sub this y equal to this back into this second order ODE with constant coefficients. Okay. So now let's call this is equation number 2. Okay. So we had equation number 1 and sub into equation 2. Okay, equation 2. Okay, so sub into equation 2, you not only need a y, you also need a y prime and also need a y double prime, right? So in this particular case, my y prime lambda this, and y double prime lambda square of this. Yeah. Okay, So derive this. Okay. Yeah, the other day I was reading a joke here. So there was a So there was a guy who kept saying, "I'll differentiate you," right? So all the polynomials trying to shy away from him because they're afraid of getting into 0, right? And then until one day, this guy bumped into exponential function. Because it doesn't matter how you differentiate it, right? It keeps itself as itself. Okay. All right, so now we sub this back into this equation here. So what do we have? We have lambda square okay? Yeah. So that's what we have after substitution. Well, that's good because all the term has a e lambda t here. So take the e lambda t out. Okay, so we get this. So let me go over the logic here, okay? I'm trying to find a solution. And based on the solution in the first order, which is exponential, so I'm sort of thinking the solution must be also in the exponential format. So this is just a guess, right? This is just a guess. So basically the guess means may not be right, may be right. So then we substitute into this second order one here. And based on our assumption, we end up with this guy here, right? So which means if I want my assumption to be right, if I want my assumption to be right, meaning I have to make this left side to be 0, right? So the only way to make my assumption to be right is what? Is to make this term to be 0. Okay? So that means because this term not going to be 0. Okay, so it means this going is 0. So essentially, if you can find a lambda, that satisfies this equation right here, then the e to the power lambda t is a solution, right? So which is actually pretty good because that means our assumption is right, right? Our assumption is right. Okay. So we need to basically solve the this quadratic equation right here. Okay. And we know the solution of this one is quite simple. We know the lambda solution is there are two solutions. It's negative a plus minus root and a squared minus 4b over 2. Okay. So the solution for this one is this. Yeah. Yeah, in general, I think what you're dealing with is ax squared plus bx plus c equal to 0, right? That's sort of in high school here. That solution is what? Negative b plus minus root b squared minus 4ac divided by 2a, right? 2a here. So in my particular case, don't confuse by the symbols here. It's 1 and here, right? Okay, yeah. Okay, now there is a very important name associated with this term, this equation right here. Okay, this is called characteristic equation. Okay, characteristic equation. Okay, you're gonna bump into this term quite a bit in the future, particularly in control system, in signal processing, and other terms here. So the keyword is characteristic. So when you describe something, you say, what's the character of that, right? So that's the important thing, that's the important feature. So in other words, the solution for the lambda here describes the characteristic of this system. Okay? So when we say, okay, what's the characteristic of the system? Basically, we're talking about in the future, we'll say how's the response of the system, right? Is it gonna be stable response? Basically, not going to go crazy, or it's going to be a crazy response, a response that goes to infinite, right? That's called unstable response. So that's the so-called characteristic of the equation. How do we know whether that system has that characteristic? We can know that by simply look at the solution of lambda at here, right? Yeah, so that's why this is important thing here. But for the time being, we don't know how do we tell that yet, but we'll look at that, okay? Yeah, we'll look at that. All right, so now things are not that straightforward at here because the solution at here actually has 3 different cases, right? Has 3 different cases. What are the possible cases at here? First of all, you could have 2 distinct real roots, right? So you could have 2 distinct real roots. Okay, yeah. So when would you have 2 distinct real roots? When what? When, yeah, that's greater than 0. Right, when this guy is greater than 0. Now when this guy equal to 0, you actually end up with 2, not 2 anymore, you end up with just 1 solution, right? So what we call that, we call that repeated, basically, we call it repeated roots. Okay, repeated roots. So that's when this guy is 0. And the last situation is related to what we just learned. If this guy is less than 0, then this square root less than 0 basically becomes what? Complex number. Yeah. So then you have 2, right, complex roots. Actually, not just arbitrarily 2 complex roots. If this term is less than 0, if this term is less than 0 here, then if you look at the solution at here, this is negative a plus minus a complex number here, right? So plus minus complex number. So the 2 complex roots are actually what? So you have basically you have like a 3 plus minus, let's see for example 2j. So the 3 plus 2j and the 3 minus 2j are so-called conjugate, right? Conjugate. So more precisely, there are 2 conjugate, okay, complex roots. Okay, so those are 3 different cases. Okay, so now we're going to look at each one of them and okay, what are the general solutions for each one of them? Okay, yeah. So let's look at the first one here. When we have this term greater than 0, so that means we got 2 distinct real roots. Okay, 2 distinct real roots. This is the simplest case. Very simple. Okay, very simple. So if this is greater than 0, that means lambda 1 and the lambda 2 are real, right? They are real. And if they're real, okay, always remember the bigger picture. Okay, the bigger picture. The bigger picture is we are letting y equal to e to the power lambda t. Basically, we assume that this is a solution here, right? And this only makes this is a solution when lambda satisfies this equation. Now that I got my lambda solution now, and for this particular case, lambda real. So that means what? How many solutions do I have? I have two solutions here, right? So one is y1 equal to e lambda 1t, and y2 equal to lambda 2t. So these 2 are 2 solutions. Okay, here are 2 solutions. Okay, so these 2 are the 2 solutions. And how about the connection between the 2? Are they linear independent or are they linear independent? Dependent or independent? They're all exponential, right? Looks like dependent, but if you multiply this k1, this k2 at here, you won't be able to find a set of k1, k2 solutions other than 0 to make that expression to be 0. Right? So you see that okay, if I let this equal to 0, Okay, if I let this equal to 0, so you look at this one here, can you find any other key 1, key 2s other than 0 to make this term to make this expression to be 0? You can't, right? You can't. So the only solution is key 1 equal to key 2 equal to 0. Okay? So this means basically y1 and y2, they are Li. Okay, they are Li. If they are Li, my number 3 theorem, right? Number 3 theorem. So you got two solutions. You got two Li. So the general solution is just a sec. The general solution is y what? Yeah. Okay. Yeah. Sure.
If it comes out like when you come out of the quadratic formula, you come out with two roots. Knowing that they're two roots, will that always make it linearly independent, or not necessarily? So because you went through the quadratic and you said we got two distinct real roots.
Yeah.
Every time you get two distinct real roots.
Yeah.
Does that mean that you will always end up with linear independence?
Yes, actually that does. Well, as you're gonna see that every cases we come out of here, right? You got two lambdas. Only the second one here is a little bit. The second one is a repeated root, so we'll talk about the second one here. But for the first and the third one, right? Technically speaking, all like this. You can y equal to e lambda 1t, e lambda 2t, and they are basically linear independent. Okay? Yeah. But the second one here is a trick one. Okay, it's a trick one. Okay. Is the first one good enough? Yeah. Yes. Okay. So the second one here, when a squared minus b equal to 0, basically you got a repeated root. Okay, repeated root. So repeated roots meaning I only have one lambda solution, right? Only have one. There's only one lambda solution. Okay. So if there's only one lambda solution, well, I guess what's the lambda solution in here? When this term equal to 0, the solution is negative a over 2, right? It's negative a over 2, okay? So that lambda equal to negative a over 2. Okay, yeah. Okay, so if this is the only solution, basically means you have a solution, e to the power of a lambda t, and which is e to the power negative a over 2t, right? That's the only solution you have here. But what we're looking for is, we're looking for a general solution. So we need two solutions, right, to form a general solution. If only one, you can't form one. So if you're saying, okay, y equal to c1, y1, so what about the c1, y2, right? I can't use this one again. If I use this one again, this y1, y2, they're not linear independent. So essentially means I need to find another y2, right? And another solution. And this y2, not just a solution, this y2 has to be linear independent from y1, right? I need to find a y2 and Li from y1. Okay? So that's what we need. Okay? And okay, so how do we find a y2 that is linear independent from y1? Well, I guess maybe you can see now is, okay, how about if I multiply this y1 with any other constant? Would that make me a linear independent solution? No, right? Okay, because if this is just a constant here, that's just multiple of that. Doesn't work. How about if I plus a constant? Okay, if I plus a constant, what happens? If I plus constant, the first question is, if I plus a constant here, will that be a solution first, right? Will this be a solution? So how do I verify that? I can plug this back to where? Back to my original equation here, right? So let's say if I do this, basically, this is basically y1 plus c, right? y1 plus c. So if I do this, what's y2? y2 is y1. y2 prime is y1 prime, right? And y2 double prime is, what's that? y1 double prime. Now if I substitute back into this differential equation there, so that's the y double prime plus AY prime plus BY equal to 0. So let's see what we get. We the y what am I saying here? Yeah. So I'm substituting y2 double prime here, right, which is y1 double prime, right? And then sub this one here, which is ay1 prime, and by. So sub this is this term here. So by1 plus c, right? This is the left side. So then for this last one here, this is a by1 plus bc. Okay, it's by1 plus bc. So then, if you look at this one here, if I just look at this whole chunk right here, what is that equal to? Yeah, that equal to 0, right? Because y1 is a solution. So you're only left with a bc. But can you guarantee the bc is 0? The only choice is what? Is c equal to 0, right? So I guess this won't work, right? This won't work. Okay? So this is not going to work. Okay? Okay, if this is not going to work, so what did I just try? I tried multiply by constant won't work, plus constant won't work. So then let's try a different thing now. Let's try, instead of multiply with a constant, we multiply the y1, okay, with a function of t. Okay? Yeah, so not going to be constant, but a function of t. So before we show that it's going to work, first logic here is, will y2 be linear independent from y1 if I do this, when v of t is not a constant? Right? So they must be linear independent. I mean, if this is a function of t at here. Okay? So that basically satisfies one of the conditions here. Then the next logic thinking is, what will be v of t such that y2 is a solution? Right? So when you let this guy here is, so this means y2. Okay, this means y2 is Li from y1. Okay, this means this. And the next one here basically is v of t equal to what? That y2 is a solution. Okay? Yeah. Yeah.
I don't understand the last two lines.
These two lines here? Okay, so first of all, I'm letting this equal to this, right? That's my logic here. Why do I do this? Because I'm trying to find the solution y2. And not just a solution y2, I'm not also trying to find a y2. It's a solution, but at the same time, linear independent from y1. Okay, that's a bigger picture. Is that good? So let's say your y1 is Li lambda t. When you multiply with a t here, for example, right? Yeah, actually it turned out to be t. Okay. So when you multiply t here, if this is y2, what is the connection between y2 and the y1? Are they linear independent? Are they linear dependent? They must be independent, right? So that basically that's good, because that means when you do this step here, that satisfies one of our objective. The second objective is what we haven't done it yet, right? It's we want to find what would be a possible solution for v of t such that it's a solution. Is that good? Yeah. So I'm not going to solve it today now, but this one here is called variation of parameters. It's a method called variation of parameters. Okay? Yeah. All right. Any questions? All good?